Welcome friends, in this video I'm going to show you how to understand the concept of a partial derivative. Again, as long as you know how to unfold a piece of paper, you'll immediately grasp this. You don't need fancy schmancy math, to be honest. We're just kind of appreciating a fundamental concept. Take a look. You see I have a grid here. When I have a grid like this, think about this for a second. I'm sure perhaps you've even done this, right? You can either unfold it this way and make it bigger in this direction, or you can make it bigger in this direction. So what I'm going to do is this. Take a look. I'm going to unfold it. And notice something important. You see it's grown by 1 along this dimension right here. The horizontal dimension has grown by 1 right here. See this? This is up by 1. When that occurs, you see that it grows by 1, 2, 3, 4, 5, 6 boxes in the area. Let me emphasize this point. Do it one more time. Take a look. I have again grown by 1 in this dimension, but this has grown by 1, 2, 3, 4, 5, 6 boxes, just like that. Let's do this one more time to drive home the point. I have grown by 1 in this dimension. I have grown by 1, 2, 3, 4, 5, 6 boxes in that area. So, what is that telling us? It's telling us that, first of all, you can take something like a grid and you can grow it in only one of the dimensions, which in this case is the horizontal dimension. You see for yourself. Let's write down this rate of growth. It's really easy. So I'm going to say here, for example, 6 boxes. Right, every time you unfold it, this goes up by 1. 6 boxes for every, for example, 1 horizontal, for example, unit. So that is what basically we would call the rate of change in this dimension. You see it for yourself. Is that the only possible, for example, rate of change? This is a rate of change if you think about it, right? Up by 1, up by 6 in the area. Up by 1 in this dimension, up by 6. Up by 1, up by 6 in the area. So that's one thing that can happen with a simple geometric shape. Take a look at it from another perspective now. I'm going to fold this back up. And now what I'm going to do is grow, for example, the vertical dimension, just to show you that it's possible to change two different dimensions. Take a look. Unfold it in this direction. So now look at it carefully. 1, 2, 3, 4, 5, 6, right? That's the original. And now this has grown by 1 in this dimension. Okay, where I'm kind of tracing with the tip of my marker. And when that occurs, the total area goes up by 1, 2, 3, 4, 5 boxes. Let's do this one more time. Take a look. Again, I'm growing only one of the dimensions, this one right here. So that's up by 1 in this direction again. And the total change in the area is 1, 2, 3, 4, 5 new boxes have popped up. Let's do this one last time to illustrate the point clearly. So I've gone up again by 1 in this dimension. And the total count in the boxes that are new is, again, 5. 1, 2, 3, 4, 5 new boxes. I could say there's a separate rate of change in this dimension. And for example, in this case, the vertical dimension, I could say that it's clearly, say, 5 boxes, right, for 1 vertical unit. What I mean by this vertical unit is this dimension right here. See, when that increases by 1, as you can see, 5 new boxes up. Take a look further. If you want to know the total, for example, increase in the area, you can just unfold everything, and you can add up the new boxes. So the ones on the bottom here, if you count them, there are 15. If you count the ones over here, there are 18. So then you can just add up 18 and 15. And we'll tell you by how much the original yellow area has grown and all. And something else to be observed here. Let me fold everything back up. This is a kind of key understanding also. When you're dealing, for example, with these individual rates of growth in two different directions, the way you see here with this. Take a look. In this horizontal dimension, and I don't have to bother the vertical dimension. You see, during this process, the vertical dimension stays constant, right? This right here, this is the vertical dimension. That's not changing. Look, I'm changing only this dimension. So this rate of growth is completely unaffected by what happens in the other way, in the other dimension, at least the way I set up my demo here. So that's one thing to be observed. And as you can imagine, you can now repeat this the other way. Take a look. So I'm going to grow only in a vertical dimension now. And when that occurs, this grows, right? This is growing. That is growing, but as you saw just now, the horizontal dimension was completely unchanged. So you can have rates of growth in different directions the way this clearly indicates, and on top of it, these rates of growth could be completely independent the way I show you here. All right, this growth in this direction is an individual rate of growth. In other words, it's called partial. The keyword is partial. Why is it called that? Because the only part that grows is this dimension, so it's a partial rate of growth. Only this part of it grows. You see that? Same thing in the other dimension. That would be a partial rate of growth because the only part of the box that grows is this dimension right here. You see that? The other one doesn't get changed, for example, the way I do it at least here. As you can imagine, thank you so much for watching. Please leave a like, and I'll see you in another physical math demonstration.